Sarah, let's begin with one of the most transformative ideas in science, spacetime.
Okay, I've heard of it, but what is it exactly? Like space and time mashed together?
Precisely. In Einstein's framework, space and time aren't separate. Instead, they form a four-dimensional fabric we call spacetime, where events occur. Kind of like a single canvas where everything in the universe exists and unfolds.
Wait, everything? You're saying like galaxies to my morning toast?
Exactly. Every moment and point in the universe has its coordinates in spacetime. Think of the canvas as stretching and bending under the presence of massive objects, much like how a trampoline bends when you stand in its center.
Oh, that's cool. So that's where gravity comes in, right? The bending?
Spot on. Now, Einstein's genius didn't stop there. He connected this idea with something called the equivalence principle. Imagine you're in an elevator that's free-falling. Everything inside, your coffee cup, your toes, even you, would float as if gravity disappeared. You've seen astronauts in space, yes?
Yeah, like everything's weightless. But why does that happen?
Here's the trick. To you inside the elevator, there's no detectable difference between falling due to gravity and the pull of an accelerating rocket far from Earth. Gravity and acceleration become indistinguishable.
Mind blown? So this free fall idea, it's like the universe's biggest cheat code?
In a way, yes. Einstein realized gravity isn't a force pulling us down. Rather, it's the bending of space-time guiding objects along curves or paths we call geodesics.
Geodesics, huh? Okay, so that's why planets like orbit stars, they're following these curves in space-time?
Precisely. Planets follow these curved paths because space-time is warped by the massive star at the center. Einstein's insight fundamentally changed how we understand gravity, from an invisible force to the geometry of the cosmos itself.
Okay, so you're telling me Einstein redefined gravity as the bending of space-time. But how did he convince people? I mean, did he just announce one day, hey, gravity's not a force, it's all about these geodesics?
Not quite, Sarah. You see, science relies on experimental evidence. One of the early validations came from Mercury's orbit. For years, astronomers noticed its precession. Basically, the wobble in its elliptical path didn't match predictions from Newtonian physics.
Wait, like Mercury wasn't playing by the rules?
Precisely. The calculations kept coming up short. But when Einstein applied his field equations of general relativity, the numbers fit perfectly. It was, for lack of a better word, a eureka moment. His theory explained this anomaly where Newton's fell short.
Whoa, so that was like the first big win?
Indeed. But the crowning moment came in 1919, during a solar eclipse. You see, Einstein predicted that light from stars passing near the sun would bend due to space-time curvature. Arthur Eddington led an expedition to observe this phenomenon.
What, like they literally looked at stars bending around the sun? That's wild.
Exactly. During the eclipse, the sun's light was blocked, and Eddington could photograph distant stars appearing shifted from their original positions, just as Einstein's theory predicted. It was concrete proof that space-time itself warps under gravity.
So that's when Einstein went from smart guy to international superstar?
Precisely, Sarah. Eddington's observation earned Einstein global recognition. Suddenly, theoretical physics was headline news. But that wasn't all. Another proof came from the effect called gravitational redshift.
Redshift? I've heard of that. Isn't it when light stretches out or changes color?
Spot on. Light escaping a gravitational field loses energy, shifting to the red end of the spectrum. This was directly measured in experiments and confirmed a key prediction. In a related effect, gravitational time dilation showed that clocks run slower in stronger gravitational fields.
Hold on. You're saying time actually moves slower in places like closer to massive objects?
Exactly. If you were near a black hole, for example, time for you would pass slower relative to someone far away. These experiments, like measuring tiny differences in atomic clocks on Earth compared to satellites, confirmed this stunning aspect of relativity.
So rad, it's like every experiment was another puzzle piece proving him right.
Well said. Each independent test fortified the foundation of general relativity, from Mercury's orbit to light bending and redshift. The collective evidence left no doubt that Einstein's picture of gravity was the right one.
It's amazing how all those experiments proved Einstein right. But here's what I don't get. Aren't scientists still finding wild new things about his theories even today?
Absolutely. One of the most exciting developments came from the LIGO Observatory just a few years ago. Physicists detected gravitational waves for the very first time, ripples in spacetime caused by massive cosmic events like merging black holes.
Wait, spacetime ripples? Like actual waves traveling through the universe?
Yes, exactly. When two black holes collide, their immense energy sends out these waves, distorting spacetime itself. It's like throwing a pebble into a pond and watching the ripples spread, only on a cosmic scale.
That's completely wild. I mean, how do you even see something like that? It's invisible, right?
Good question. What we see isn't the waves themselves, but their effects. LIGO uses incredibly sensitive detectors that can measure tiny distortions, down to less than the width of a proton. It's a testament to human ingenuity, really.
I can't believe we can measure something that small. So what have we learned from those waves?
We've confirmed Einstein's predictions yet again, but we've also gained a new way to explore the universe. Gravitational waves give us insights into events we couldn't detect before, like merging black holes or even neutron-star collisions.
Okay, this is blowing my mind. And what about the big mysteries? Like, I've heard of dark matter and dark energy. Do they fit into this space-time picture at all?
Ah, the great enigmas. We know dark matter and dark energy shape the universe in profound ways, but their nature remains elusive. Dark matter, for instance, seems to interact only through gravity. It's like an invisible scaffold holding galaxies together. And dark energy, well, it's the force driving the universe's accelerated expansion.
So they're like, these cosmic mysteries Einstein's theories can't fully solve yet?
Precisely. General relativity explains how space-time behaves, but it doesn't tell us what dark energy and dark matter actually are. And on an even deeper level, there's the challenge of reconciling relativity with quantum mechanics, the theory governing the tiniest particles.
So physics still has its work cut out, huh?
Oh, absolutely. But that's what makes science exciting, the endless questions. For instance, general relativity underpins our understanding of the Big Bang and how the universe began. It describes an expanding cosmos, but the journey to fully comprehend it, that's still ongoing.
It's kind of inspiring. Like, Einstein gave us this insane core idea, but there's still so much left to figure out.
And that's the beauty of it, Sarah. Einstein's legacy isn't just his equations, it's the curiosity he sparked. Every new discovery, whether it's gravitational waves or the search for quantum gravity, builds upon his work, guiding us closer to understanding the universe's deepest secrets.
Wow. I can't wait to see what we figure out next. This whole journey, from planets orbiting curves in space-time to ripples from black holes, is just mind-blowing.
It truly is. And that's what makes science so thrilling, the realization that there's always more to discover. On that note, Sarah, I think we've reached a good stopping point for today's journey.
Yeah. Thanks, Professor. This has been amazing. Seriously, I feel like I'm looking at the universe in a whole new way.
The pleasure's mine, Sarah. And to our listeners, thank you for joining us in exploring Einstein's incredible legacy. Until next time, keep asking questions and looking up at the stars.